Hello, welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue talking about recursive functions that use the call stack, that call themselves more than once. And we're going to start with kind of the most basic example of this, the example of Fibonacci numbers. Now in a certain way, Fibonacci numbers are a really horrible example, but we're going to use them anyway. And the reason we're going to use them is simply because while they are not necessarily using recursion isn't necessarily an efficient way to calculate them or how you really want to calculate them. They're a very simple example which I believe can help to illustrate the fundamental aspects of recursive functions and show you how to think about them and how to deal with them. So the idea of the Fibonacci numbers is that it is a sequence of numbers that can start with any two numbers you want. Typically this starts with two ones. And then every number in the sequence is the sum of the previous two. So the next number is 2, followed by a 3, followed by a 5, followed by an 8, 13, 21, etc. Okay. So that is the Fibonacci sequence. And what I want to do is I want to write a function that does this. So in describing it, I kind of built things up from the bottom. But we can also describe this in a recursive way, which is to say that, so if we give these indices, this is index 0, this is index 1, this is index 2, 3, 4, etc. We can define this recursively as the nth Fibonacci number is equal to, well, if n is less than 2, then we're getting back those ones at the beginning, else it's the sum of the two Fibonacci numbers before n. So the fib of n minus 1 plus the fib of n minus 2. Okay, so that's a kind of a simple mathematical declaration of the Fibonacci numbers with a little bit of kind of a Scala syntax thrown in. And we can take that and put it into a program. So I can say fib of n, which is an int, returns an int, equals if n is less than 2, 1, else the fib of n minus 1 plus the fib of n minus 2. So this function calls itself twice. And that's a little bit different than anything that we have seen in the past. When we did recursion for iteration, it was always the function called itself once, and then that function called itself once, and that function called itself once. And when you do things that way, the calling pattern works very much like a loop. So anytime when you write a function, a recursive function, it calls itself only once, turns out that function is very easy to convert over into a loop. Where things get harder to do with loops is when the call stack becomes involved and the function calls itself more than once. Now, what do I mean by saying that the call stack is involved here? So to understand this, let's go back and I put in n of 5. Let's go ahead, I'll play with n of 5. This is actually possibly a little bit larger than what I really want to do here in the video. To make it so it's not so long, I'm going to stop where I'm not going to write the n equals in here. So n of 5 is equal to n of 4 plus n of 3. So it calls itself first with 4, and then it sits there and waits, and it remembers that it still needs to calculate n of 3. But it's waiting on the result of n of 4 first. And the n of 4, I'll leave that uppercase, the n of 4, well, the first thing it does is it does a check to see if we're less than 2, and because we're not, it calls itself with n of 3. Which is not less than 2, so it calls itself with n of 2, which calls itself with n of 1. Now, at this point we're less than 2, so this returns back a 1. So I'm going to remember that 1. So this is our n value, and this is the return value from the first recursive call. But then it also calls itself with 0. And that 0 is less than 2, so it returns a 1. So we get 1 plus 1, and that is what is returned back up the call stack. So the 2 returns, and then our 3 gets the value from 1 plus 1, which is 2, and then it calls itself on n equals 1, because it called itself on the 3 minus 1, now it calls itself on the 3 minus 2. This, of course, gives back a 1, and so we get that the third Fibonacci number is 2 plus 1, so a 3 gets returned back up the call stack to the 4, and that was the result of n of 3, and now we need to do n of 2. So n of 2, well, calls n of 1, which returns a 1, and then it calls n of 0, which also returns a 1. So then we add those together and we get 2, and so we have a 3 plus 2 here, and that adds together and we get 5. And so we've popped all the way back up to the top of the call stack where we have our 5 waiting, but that was only the result of n of 4, so now we need to calculate n of 3, which calls n of 2, which calls n of 1, and hopefully you can kind of see where this is going. So notice that what happens is the call stack gets longer and shorter and longer and shorter. And it goes back and forth until finally we get that we have this will come all the way back up, and when it does, because the third Fibonacci number is 3, we get 5 plus 3, and the entire function returns 8. Okay, so that's how that would work actually on the stack. But it turns out that when I'm trying to think about what's happening inside of a recursive function, this is not a very good way to think about it. What works better is to picture this in a different structure, a structure called a tree. And the problem with doing it with the stack is that I kept erasing things, and that whole erasing of stuff, well, once you erase it, it's easy to forget what was going on there. So instead of erasing stuff, what I want to do is I want to draw this out in a different approach. So the 5 calls the function with the value 4. Okay. And then the first thing the 4 does is it calls with the value of 3, and the first thing that 3 does is it calls with the value of 2, and the first thing that 2 does is it calls with the value of 1. Move these things up a little bit. And then this returns a 1 back up to here. But this also has to call itself a second time, and so it calls with the value of 0. And it's helpful here to draw some connections between these things. So the 2 called there and there, the 3 called the 2, the 4 called the 3, the 5 called the 4. We'll drag these things around a little bit, space it out somewhat. Now, of course, at this state, the value for the second Fibonacci number would be done, and that can return. So this returns 1, this returns 1, and then the value that comes back up to here is 2. But this still has to do another recursive call, and so it calls the Fibonacci with a 1. We'll draw a nice little arrow from there to there. And this returns a 1, so we have the 2 and the 1, which adds to 3, and that calls up to here. And now the 4, since we've completed the 3, also has to call itself with 2. And so we have a recursive call with 2. Now the recursive call with 2, and actually I should space this out a little bit, because the recursive call with 2 makes its own recursive calls with 1 and with 0. Each of those returns a 1 back up the call stack. And so 1 from here, they get added together to give you 2. That 2 gets returned up to here where there was also a 3 waiting, and so this gives us a 5, and so a 5 gets passed up to here. And then this has to call itself with 3. Now in this case, I can notice, hey, look at that. This was a call with 3, and it's going to do exactly the same thing it had done before. So I can copy that entire subtree here. Let's drag the 5 over more towards the middle there. And then the 5 calls itself, the 5 calls the function with 3, which calls the function with 2, which calls the function with 1, which returns a 1, and then it calls the function with 0, which returns a 1 and adds them together, and it returns a 2 up to here, then calls with 1, and that returns a 1, which gives these get added to give you a 3. The 3 gets returned back up to here where there was a 5 waiting, and it adds together and it gives you 8. Okay. By drawing this as a tree, we can see every single call that went through, whereas the stack we see things being erased and reformed. If you have to trace a recursive function that calls itself more than once, I highly recommend that you draw something out that looks like this. And in fact, if I were doing this on paper, I often label the arrows going back up. In fact, can I? Yeah, so there we go. So that returns 1, and that returns 1, and the 1 and the 1 get added together to give you 2, and this returns 1, and so now I have a 2 and a 1, and they get added together to give me the 3, and this returns a 1, so now I have that will wind up returning a 2, but I don't have that yet. I have the 1 from here and the 1 from here. Those get added together to give me a 2, and so those get added together to give me a 5. This calls down here, calls down here, calls down here. This gives you back a 1. This gives you back a 1. Those get added together to return the 2. This returns a 1. Those get added together to return a 3. And the result of the entire calculation is, of course, 8. Okay. So that's one way of drawing this out. And when you're tracing recursive functions, this can be a very helpful thing to do. Now, a lot of times, these trees are going to get so big that you won't wind up wanting to draw out everything, but it can help you to understand what's actually going on in there. Now, why did I say earlier that this wasn't very efficient? Okay, so we can put in some print lines here. Print line fib of 5. And if I do a Scala on that function, or on that script, this should print 8. What about a of 15? Well, okay, that's a bigger number. What about of 50? So we get the 8, we get the 987, and then we're waiting. Okay, and the problem is that as this is written, as you saw when I was drawing this out, we have these significant amounts of subtrees that are being recalculated. So 5 wound up calculating the Fibonacci of 3 twice, and 6 winds up calculating the Fibonacci of 4 twice, which means that you're calculating the Fibonacci of 3, more times, etc. So it turns out that every value is being, especially the lower values, are being calculated many, many times. And so this will take quite a while. So while that's working, I just want to note that we could do this more efficiently. One way would be to do this with a loop, in which case it will not be, not only is it not recursive, it's not going to be functional. So I want to make variables a and b and set them both to 1. And then let's put on an if in the front here just to keep my logic simpler. So if n is less than 2, I'm going to return 1. Else, I'm going to set up an a and a b and a c. C equals a plus b. Hey, look at this. This finally finished over here, and it overflowed my integers. So it is a very big number, but it was slow. We could, of course, make this so it can calculate those things, possibly by setting these to be longs or setting them to be big ints. Don't think I want to calculate fib with big int. Let's just go with long. And rerun that, and it will. Oh, I'm in the middle of writing this, so it's not happy. And then what happens in here? Well, I can write a for loop that says that for I in 2 to n. Believe that would give us the correct logic. We can check it if not and change things. Then I want to set a equals b, b equals c, c equals a plus b. Yep, and then let's return c. Copy those lines, paste them down here. Actually, it occurs to me I should probably flip the orders of these, because we know this call right here is very slow. So delete those lines, paste it down here. So the first thing is we want to check to make sure that it's correct. Oops, we're off by a little bit in here. We're going too many iterations through this. So let's make sure what this, okay, so yeah, so if I pass in a 2, I don't want this loop to go at all. So it should just give me back the a plus b. If I pass in a 3, I feel like that looks like it was going oh, and I have a typo. This is one of these places. I actually enjoy programming in front of the class in my classes, just because it becomes a challenge for them to make sure. Okay, so, and of course this version still uses ints. And let's make sure that these are all initialized to be longs instead of ints. Okay, so yes, big number. You notice that just popped out immediately from doing this, because it turns out that if you use a loop to do this, it's not nearly as slow. It doesn't have to be a loop. We can do this in a functional way with recursion, where I do something like fib recur of n, which is a long, and we'll return a long. And I'm going to define, so I'll say let's define a helper function, def helper. Let's go with an n value. Once again, actually we'll go with an n value, which is a long, an a value, which is a long, and a b value, which is a long. And this is going to give us back a long. And what it happens is if n is less than or equal to 0, then we give back a plus b. Otherwise, we call the helper and we give back, or we call it with n minus 1, comma b, comma a plus b. So that's where our c would come in. If n is less than 2, we give back 1, else, well actually I don't even need that, else we'll give the helper function called with, and I believe I want to do an n minus 2 because we're terminating at 0. I could theoretically terminate that earlier. And 1 and 1. We'll see if that 3yy, paste. Okay, hey, that did eventually finish and it got the same answer, which is nice. This might be off by 1 on the recursive value. Oh, it's not. That gave us the same answer. So even using recursion, notice that also returned immediately. But the recursive version that branches does not. So that is the fundamental problem with this version. While it's a great example for showing you how recursion branches and how the values get returned back up, it turns out this is a horrible way to solve for Fibonacci numbers. So after this video, we're going to look at other problems that actually kind of need the recursion more than what the Fibonacci numbers did. But I wanted to start with Fibonacci just to help you see and understand what's going on.